Welcome to my Introduction to Networking course, typically abbreviated ITN. This will be for the CCNA version 7 curriculum. Module 12, IPv6 addressing. So we're going to be looking at, first of all, what are the issues with IPv4 that made us move to IPv6? We're going to talk about IPv6 representation, addressing type. Then we're going to look at the types of addressing, global unicast addressing and link local addressing, similar to private versus public addressing for IPv4. Then we're going to talk about the dynamic addressing for public unicast addresses in IPv6. But that's not all. We also then will talk about dynamic addressing for link local addresses, multicast addresses, and then we're going to talk about subnetting in IPv6. Though subnetting in IPv6 is way simpler than subnetting in IPv4. So jumping right on in, IPv4 issues. In the previous lecture, we talked about the different words that actually assigned our IPv4 addresses. And that meant we're also looking at how many addresses those words gave the different groups. How many were sent to North America, South America, Africa, Asian Pacific, and Europe and Russia. Well, the problem with that is these addresses were exhausted already. You'll notice a lot of these dates are 2015, 2012, 14, 11, 2020. All of these have already passed. So that means almost every country has already exhausted all of their IPv4 addresses. Hence the need for IPv6. IPv6 has a much larger address space. IPv4 was 32 bits, and that gave us roughly 4 billion addresses. While IPv6 is 128 bits, and that gives us roughly 340 undecillion addresses. So why do we need so many addresses? Well, one, before we had a typical house having 5 to 10 IP allocated devices. But with the growth of IoT, with the growth of smart devices, we're now seeing homes needing 50-ish addresses. Smart TVs, smart refrigerators, smart washer dryer, IoT-based cameras, smart TVs, and so forth. So we needed something that was going to give us additional addresses. So why the drastic jump between 32-bit and 128-bit? Essentially, they wanted to ensure that there was plenty of addresses for growth. So we wouldn't have to do this in the next 20 years again. IPv4 and IPv6 can coexist. You can have both running simultaneously. This is called dual stack. You can also have an IPv4 network transmitted over IPv6 and vice versa. Those technologies are called tunneling and translation. If we're looking at transporting an IPv6 packet over an IPv4 network, that's tunneling. If we're talking an IPv6 enabled device communicating with an IPv4 enabled device, this is called translation. So let's go ahead and let's talk about address representation. How do we represent 128 bits? We no longer do this in binary. We actually do this in hexadecimal. The IPv6 addresses are not case sensitive, so uppercase, lowercase doesn't matter. It's all the same. The preferred format for writing an IPv6 is there will be 8 groups of 4 characters separated by colons. This is called a hextet. And again, this is unofficial. 4 characters per hextet because each character is a base 16 number. It's a hexadecimal number, or 4 hexadecimal values. So for example, we have 8 strings of numbers with each string being separated by colons. So 2001 is the first hextet, 0db8 is the second hexstat, and so forth. So you'll notice we have a large string of zeros also. So that makes writing these addresses a little harder. So there are rules that we can look at when talking about our addresses and how they are displayed. So rule number 1, when we have a long set of zeros, we can actually remove leading zeros. When we have an entire hextet full of zeros, we can, in one of them, shorten them. And that's actually rule 2. But sticking with rule 1, only leading zeros can be removed. So here, when we have a long string of zeros, 2001, 0, db8, 000, well, those zeros can actually be just shortened to 1, 0. And in the 5th, 6th, and 7th hextet, you'll notice again all zeros. So we have that long string of zeros. With that long string of zeros, we can actually remove them and replace them with double colons. So colon is a way to denote all zeros in those areas. We know that there are 8 hextets. So when we see a double colon, that means all of the remaining hextets between those double colons are zeros. So first and second and third hextet, actually I'm going to grab my pen so we can do that. First, second, third, fourth hextet are all zeros. And the 8th hextet is that 200 number. So that means the remaining 1, 2, 3, 4, the remaining 3 hextets in that double colon are all zeros. Again, this is 8 groups of hextets. So 1, 2, 3, 4, and we had that one. So that meant the remaining 3 hextets of all zeros were replaced by that double colon. You can only use a double colon once. That way there is no misconstruing what those double colons mean. If we had double colon, a hextet, and double colon, we don't know the number that would fall in between each set of the double colons. That is why you can only use them once. Alright, moving on is address types. In IPv4, we talked about characteristics, multicast, broadcast, unicast. Well, in IPv6, we have unicast, multicast, and anycast. Unicast and multicast are pretty similar. We no longer have broadcasts. That has been replaced with an anycast. Anycast basically is any IPv6 unicast address can be assigned to multiple devices. Basically, a packet is sent to an anycast address is routed to the nearest device having that address type. So you can have multiple IPv6 addresses assigned to devices. So unlike IPv4, IPv6 doesn't have a broadcast address. We already know that. There is a IPv6 all-node multicast address that essentially is the same thing. So there's an all-node multicast that will act like a broadcast. Address types, we have to talk about prefixes. So again, here we have, similar to IPv4 when we talked about networking and host bits, here we have a prefix and interface. When we're dealing with the prefix, that is typically the first 64 bits of the network. That's what we would classify as the network bits. The interface ID is very similar to the network. Prefix is going to be the network. Interface will be the host bits. It is strongly recommended that when we're dealing with 64-bit interface IDs for most of the networks, this is basically done because SLAC, stateless addressing auto configuration, will use 64 bits for the interface ID. Makes it a little easier. also it splits the addressing in half. So the first 64 bits will be given to the network portion. So types of addresses. With a IPv6 unicast address, we have several special types of address. A global unicast address, GUA, G-U-A. We have a link local address, LLA. We have our traditional loopbacks, unspecified addresses, unique local addresses, and other embedded IPv4 addresses. The large two that we need to understand the most are global unicast addresses. This is most similar to IPv4 public addresses. They're unique and internet routable. And we have to understand our link local addresses. This is required for every IPv6 device on the network. And basically, link local addresses are not routable. And these are very similar to private IPv4 addresses. The nice thing with IPv6, it does have a unique local address ranging from FC00 to FDFF. So that entire range, FC to FD, have a very specific functionality. This is going to be more of the private addresses for IPv4, but they're not exactly the same. I understand that link local addresses are also similar to IPv4 or to the private addresses, but again, they're not quite identical. Here, FC to FD are going to be the most like private addresses. They are unique local addresses used for local addressing within a site or between a limited number of sites. Unique local addresses can be used for devices that will never need access to another network. Unique local addresses are not globally routed or translated to a global IPv6 address. That is the key takeaway. These types of addresses cannot be translated to a global address, where a link local address can be translated. Looking at an IPv6 GUA address, basically, it was designed in such a way to allow a very limited number of GUAs to allow on the internet at this time. Basically, we are looking at the first 3 bits of any IPv6 address. So only the first 3 bits that begin with 001 are allowed to be assigned. That means they will start with 2000. Currently available GUAs with a decimal of 2 or 3 are allowed. Basically, that took all of our addressing, and that means only 1/8 of the current addressing space is allowed on the internet. This is done on purpose. This means that there's plenty of room for growth. They're not just wasting addresses for the sake of wasting addresses. Normally, global unicast addresses will start with 2000. Alright, the GUA structure. We have our global routed prefix. That should be our first 64 bits. We have a subnet, and basically the subnet field is with the area between the global routed prefix and the interface ID. This is used to organize the overall addressing space and identify the appropriate subnets within that location. The interface ID is the remaining 64 bits, and that's going to be more of the host portion. So the prefix can actually be the prefix and the subnet length. Those combined will be the first 64 bits. The remaining 64 bits will be the host bits or interface ID. Moving on, we have to understand our link local address. Our link local addresses, basically packets with the source or destination of a link local address, cannot be routed. They have to be sent to a default gateway. If it needs to leave the network, it will be masked to a global unicast address. Every IPv6 enabled network will have a link local address. If a link local address is not configured on the interface, it will automatically create one. Basically, link local addresses are in the FE80 range with a prefix of /10. That means the first 10 bits do not change. Realistically, FE80 is what you would always see as the beginning for a link local address. Next section is about how do we configure both global unicast addresses and link local static addresses. Alright, so what you end up having to do is you navigate to an interface, and just like you would an IPv4 address, you type IPv6 address, give it the address, but you'll notice this is going to be in / notation. And then of course you turn it on. The assumption is you've already enabled IPv6 global unicast addressing on the router or on the device itself. So you have to make sure that IPv6 is already on. Similar to IPv4, with all of the commands that involve IP, if you add the v6 to it, almost always it will work. And again, don't forget to use the question mark if you're not sure the syntax of the structure. Like again, IPv4, you do the IPv4 address, you'd put the IP address space, in dotted decimal form the subnet. With IPv6, you're using / notation. That's why I'm saying you can always use a question mark to figure out how the command should go. If we're looking at a in device, again, you will have the same thing. You'll have the subnet prefix length, you'll have the addressing, you'll have the default gateway. You can also have this set for DHCP or Slack if you're being used. Again, you're going to have a automatically assigned link local address, or you can define it yourself with the IPv6 address and then put the address in and you denote it with a link local command. This is basically allowing you to configure it manually without having it auto-configure. So, dynamic addressing for global unicast addresses. Devices obtain these addresses dynamically through ICMPv6. There are a few router characteristics that we have to understand how these addresses actually get obtained. Router solicitation and router advertisements and router acknowledgements. So a solicitation messages are sent by the host to discover the routers. Router advertisements are the messages sent by the routers to inform the hosts how to obtain that information. Part of that information will include things such as the network prefix and the prefix length, the default gateway address, if there is DNS addresses available, the domain name, if available. The router advertisements provide 3 methods for configuring the address. Slack with a stateless DHCP server, or stateful DHCP with no Slack. Remember, Slack is the auto configuration, and don't worry, we're going to discuss all 3 of these in depth in the upcoming slides. Alright, so method 1, Slack. So Slack allows the device to configure a GUI without the service of DHCP. The device will obtain the necessary information from the configuration from an ICMPv6 router advertisement message from the local router, the local layer 3 device. Basically, the prefix is provided by the router advertisement, and the device will either use a EUI64 or a randomly generated method for the interface ID. A EUI64 basically looks at the MAC address, and then it sticks FFFE in the middle, and it will flip one additional, I believe it flips the 7th bit of the MAC address, and that is what creates the EUI64. Method 2, Slack and the stateless DHCP. So again, router or device comes online, it will send a router solicitation. The router solicitation will go to the local router. The local router will send a router advertisement saying, hey, this is where information that I have. And then the router advertisement will also give the default gateway, and then the rest of the configuration will be sent to the stateless DHCP server. Essentially, the router says, here's my information, here's the information for the DHCP server, get the rest of it from the DHCP server. And the DHCP server is going to be things like DNS, the domain name, and information like that. The third method is a complete stateful DHCPv6 deployment. Basically, device will come online, we'll send a router solicitation. The router acknowledgement, or the router advertisement, the RA message, will suggest that the device use the following information. The router link local address, which the RA sources the IPv6 address for the default gateway, and then it will also then say get everything else from the DHCP server. So the stateful DHCP server will obtain the address, the DNS information, domain name, and any other information. So stateful DHCP will use the link local address of the router, and everything else comes from the DHCP server. So we already talked about the EUI process a little bit. So how is this going to work versus a randomly generated interface ID? Again, the interface ID can either be done those two ways. So the EUI process is it will split the MAC address in half and will add FFFE in between, and then it will also flip the 7th bit. So basically the 7th bit of the MAC address is reserved from the binary 0 to 1. So it flips it. A randomly generated interface ID will depend on the operating system, and instead of using the MAC and the EUI64 process, it will just essentially create a randomly generated one. Beginning with Windows Vista, Windows uses randomly generated instead of a EUI64. Keep in mind that IPv6 does have a duplicate address detection. This is very similar to ARP and IPv4 to verify that no two devices have the same global unicast address, or there are not duplicate link local addresses on the same local network. Moving on, we have our dynamic addressing for IPv6 link local addresses. Alright, so first and foremost, all IPv6 interfaces have to have a link local address. The link local addresses can be configured dynamically. They are created using a FE80::10 prefix, and they decide to use the EUI64 process more often than not. Though sometimes they can use a randomly generated number depending on the operating system. Here we have an example using Windows. I believe it is Windows 10 in this example, where you can see the similarities between the MAC address and the IP address, the IPv6 address. So that is how you can tell if it's using a EUI or if it's using a randomly generated one. Because again, if it's randomly generated, then they're not going to see the commonality between the addressing and the MAC address. Or you will not see that FFFE in the middle. That's another dead giveaway. So Cisco routers automatically create a link local address whenever a global unicast address is assigned. So they end up with both. The Cisco iOS will use a EUI64 to generate that interface ID for all of the interfaces it has. If we look at this example, they're looking at gig 000 on the device, and you can see the link local address, and you can compare that with the MAC address. Again, the MAC address is split in half, FFFE is inserted in the middle, and the 7th bit is flipped. So you can see the function, you can see the similarities between the link local address, the FE80 address, and the MAC address. So okay, that was. Oh, you can also do the show command to verify. You can do a show IPv6 interface brief, and that will show you the IP address. If you do a show interface and give it the appropriate interface, you can see the MAC address. We have a packet tracer lab to show and do the configuration for IPv6 addressing. We have the next section, which is all about multicast addresses. And again, a multicast address will have a prefix of FF00. There are two types of multicast addresses: a well-known multicast address and a solicited node multicast address. It's important to note that multicast addresses can only be the destination address, not the source. Typically, the source will always be a unicast address. So a well-known IPv6 multicast address. There are certain types of groups that are reserved. Basically, they're predefined groups of devices. Here are two common multicast groups. FF02::1. This is an all node for multicast group. This is the multicast group that all IPv6 able devices will join. We also have the FF02::2, which is the all router multicast group. This is basically the multicast group that all IPv6 routers will join. You remember that you have to turn on IPv6 addressing by issuing the IPv6 unicast routing command in the global configuration. The command is IPv6 unicast TAC routing. That enables IPv6 for that device. Again, these are just two of the multicast groups, not all of them. Remember that with an IPv6 interface, it will have multiple IPv6 addresses assigned to it, and that includes the multicast group addresses. And again, this is a well-known review for multicast. The next one is going to be solicited. A solicited node multicast address is similar to an all node multicast address, which is similar to a broadcast. A solicited node multicast address is a map to a special Ethernet multicast address. The Ethernet NIC can filter the frame by examining the destination MAC address, without even having to worry about sending the IPv6 process to see if the intended target is IPv6. We have a lab identifying the appropriate addresses. Moving on, we have our subnet for an IPv6 network. Again, we've already talked about the 64-bit prefix and the 64-bit interface. The prefix will be part of the global routing prefix and the subnet ID. That will determine the overall 64-bit prefix. Basically, a separate subnet ID filled in the global unicast address portion will be created. This creates the subnets. Here we have all of the different subnets. We have a /48, so the first 48 bits are the same. Only the next 64 bits are going to be different, and that will create additional subnets. Remember that the prefix is the first 64 bits. On the screen, the diagram shows the 64 bits, with the last 16 bits being the varying bits or the subnet bits. So in the example topology, it will require 5 subnets. So we will get 5 subnets, and we could identify them and we can distribute them. How do you do the router configuration? We've already shown how to configure an IPv6 address. You have to make sure to enable the interfaces as well. And that is it for this course. For this lesson. We have a few additional labs looking at IPv6, determining, configuring, and verifying, setting up, and verifying again for IPv6. In this lecture, we talked about issues arising from IPv4, why IPv6 came about. We talked about the overall characteristics and structure and the anatomy of an IPv6 address. We talked about the 2 main address types, global unicast address and a link local address. We've talked about how to configure addresses. We talked about how ICMPv6 messages are used for router solicitation, router advertisements. We talked about dynamic address assignment using Slack with stateless DHCP, and the third method being stateful DHCP. We talked about multicast addresses and IPv6, both well known and unsolicited, and we ended with discussing how to configure them. That is it for this lecture. If you have any questions or concerns, please reach out. Thank you.